So if we go to Amazon SageMaker, we go to Notebook Instances. We'll open tutorial page, or the tutorial notebook instance. Stop this one. Sounds good. And should have the familiar Jupyter dashboard page, right? I said we'll probably use Jupyter Lab for this. Sometimes Jupyter Lab functions a little bit better in conference sort of slow internet settings. It's also, like I said, a feature we're kind of rolling out now. Jupyter Lab is still in beta, but a lot of people really, really like the interface. It feels a little more like an IDE than Jupyter might. It's got a little bit more kind of functionality in terms of organization and things like that. But to get there, all you have to do is a quick URL hack, which is, you can see the URL ends in /tree ? Just delete tree and type lab. Delete tree and the question mark and type lab, and then hit enter. And when you load back up, it should load back up in the lab. The promo code didn't work? Now we are logged into our Jupyter Notebook, and we're at Jupyter Lab. Everybody still pretty much following along? Okay, good. Then I'm going to just kind of hit the stride from here. Scroll down to the bottom and open up a new terminal. Okay. And you'll notice that you're in home EC2 user. We're going to cd into SageMaker. SageMaker is actually where Jupyter Home starts. Starts one directory up from home EC2 user, or one directory past. And then we will do AWS S3 CP S3 / SageMaker -conferences -Oregon, buckets in Oregon, and O'Reilly AI sf.tar.gz/. Okay, let me move that back so that you've got full screen on my text. Hit enter. That'll take just a second. There we go. And now we're downloaded, right? And now if you go back to those files, you can see the tar gzip sitting right there, right? tar xzf O'Reilly. And now we can see 3 folders: Blazing Text, Fast AI, and TensorFlow. Okay, so we'll start with the Blazing Text example. Okay, and here's where I'll start to do a little bit of cooking show magic. You'll notice that when you open up Blazing Text, all of the example notebooks, when you open them up, they're already kind of filled out for you. They've been run through once. And so if for some reason you decide you just want to sit back and learn and not run interactively, that's totally fine. You can do that and just look through the examples as they stand. If, on the other hand, you want to walk through them interactively, you can do that. You can run the cells as you go. You can also, if you get lost easily, you can also duplicate it. So you can duplicate that notebook, and then you can do something like, restarting the kernel and clearing all the outputs. And now you've got 2 copies, one that's filled out, one that's not filled out. So you can kind of, follow along and then sit back and then follow along and all that kind of stuff, right? So whatever works best for you, I think, is the end statement, right? So it sounds like a lot of you guys have worked with Jupyter before, but just as a real quick introduction, we already showed how to open the terminal. We showed how to get to files through this file browser. You can always go check what's running over here, even if you close a tab. So I can close my terminal, and then I can always get it back, right? We can look at different commands if you really want to get into keyboard shortcuts, and then go through your tabs, right? So it's a pretty easy interface. You navigate this way, and then these notebooks are really your means of interactively running code, looking at documentation, etc. So I'll minimize that to focus on actual code. How's text size for everybody? People in the back can read? Good? Okay. So I should mention that we have, when you spin up a SageMaker notebook instance, we have a whole bunch of example notebooks loaded for you, right? So let me open this again and show you kind of what it looks like. You've got this tab called SageMaker Examples, right? So if you ever want to go back in and do examples that we didn't cover today, you can. There's a host of them there. So there's different ones on introduction to how to apply machine learning. There's ones about the SageMaker Python SDK. So this is how to use our deep learning frameworks for the most part. Then there's an introduction to the built-in algorithms. So we have a notebook here for each one of our customized built-in algorithms, showing how to use that. We have advanced functionality. So this, talks about how to get data from Redshift, or use KMS keys for encryption, or use some of the other functionality, bringing your own R container, right? So we talked a little bit about that flexibility. And so that shows that. Some more scientifically focused ones. Some that show how to use SageMaker Spark using PySpark. And then others that do hyperparameter tuning. So you've really got a large number of examples here. Those are also available on GitHub at GitHub Amazon-SageMaker-examples. So if you're ever want the kind of latest and greatest, or just kind of want to look at them without a functioning notebook instance even, GitHub does a pretty good job of rendering the Python notebook, right? So you can always kind of go through and check those out. Okay. Back to blazing text. Okay. That's the one I want. All right. So blazing text is a word-to-vec algorithm. We talked about that a little bit. We talked about word embeddings. The idea is that words that appear close to one another, and whether they're predictive of words nearby, and then using that information to generate embeddings for each word, such that each word exists in a numeric feature space where similar semantic and syntactic words are located close by one another. So we're going to do an example notebook that shows how to use blazing text, which is a really fast implementation of word2vec. It's an implementation that you can use on CPU or on GPU. It also supports like distributed CPU training, and so it's really a very fast and flexible and scalable implementation of word2vec. And so it's an easy way to get started with an algorithm that not everybody kind of knows how to use. So pretty much every SageMaker notebook starts the same way. We provide a little bit of setup information that we need. We have some libraries we're going to import. We are going to run this role equals get execution role, right? So get execution role comes from this SageMaker library. That's that SageMaker Python SDK that I mentioned, which wraps up a lot of the AWS-looking APIs into a more data science-friendly means, and has a lot of helper functions that you can use to kind of get started. But all get execution role does is returns the role that is associated with the notebook instance that you're logged in on, right? So that role that you created. And those IAM roles really help with permissions, with what data can you access, and what properties can you run within SageMaker, right? So we kind of create this role variable, and then we specify our bucket. In this case, we're just going to use a default bucket. That default bucket is going to look like SageMaker-our region-our account ID, AWS account number. But again, when you're doing this in practice, you'll probably change the bucket to wherever your data is living. Okay, so we've done that. Now we'll go get ourselves a data set. And notice one of the cool things about Jupyter Notebooks, for those who aren't familiar with it, we were writing Python up here because that's what kernel we're in. We're in the Python kernel. But we have a cool functionality with Python where we can do exclamation point and just run a shell command, right? So you can see we did that. Now we'll unzip this. Let's take a quick look at what's called text date. Okay. It's code on the fly. So looking at the top 10 lines of that file. Oops, I probably shouldn't have done that. I think this text data is a little bit large. So not a huge data set, but large enough that it created a little bit of friction there. Okay. So basically we have a text data set. You can kind of, uh-oh. I shouldn't have done a head on that. I should have limited the number of characters. It's one big large text blob, I think, in that data set, and so created a little hassle there when I did the head. But either way, you can understand that text date is just a big blob of text, and we're going to send that up to S3. Whoops, that's why, because I didn't run the. I'm doing my cooking show magic, and that's not working. Here we go. All right, this one's better. Okay, so I'll unzip that. I'll send my code back, or my text data set up to S3. As I mentioned with SageMaker, when you kick off a training job, we go provision new instances for you. We load data in from S3. So even though I can kind of pull the data with a wget down to my notebook instance, in order for my training instances to get it, I want to first send it to S3. So I send that to S3. I create an output location. So this is just an S3 path where I want my model artifacts to go at the end. And then I set up my training, right? So let me just go back and see if, good, okay. This one finally finished. There we go, short that down. Okay, so we'll run that, get the training channel, get our output location. All right, now we want to get our region name, and we use that region name because we really just want to get the container for our blazing text algorithm. So as I mentioned, everything in SageMaker is just a Docker container, including our built-in algorithms. So when you want to run a built-in algorithm, you're going to point to the Docker container location. And we have a helper function that gets that Docker location for you called getImageURI. But this is just in an account that we've created in SageMaker. And it's just a Docker container called blazing text, right? So every time you want to use SageMaker, algorithm code lives in a Docker container. So we get that specified. And then we're going to go through and start to train our model, right? So what we do first is we create a SageMaker estimator. This is where things start to look more like scikit, as I mentioned earlier. We're going to point it to a little bit of key information here first. We're going to point it to that container that we specified. So that was that image path, that ECR Docker repository image path. We're going to point to the IAM role that we want to use. That's going to control our permissions to our data. We're going to give it hardware requirements. So in this case, we're going to train with 2 instances of C4 2x large. It's not a giant data set, but it's big enough that we'll still kind of show off the distributed training portion. And then we can set up a couple of optional parameters here, like volume size, right? We only want 5 gigs. For an EBS volume, because our data set isn't huge. We could set that to 16 terabytes if we wanted to, if we had a really large data set that we wanted to control the EBS volume on our training instance. How long our max runtime is, so if we wanted to constrain, if we were worried our algorithm is going to run too fast, this is going to run in 100 seconds or 300 seconds, so we don't have to worry about that. But Input mode, file, this is where I talked about file and pipe mode, where we either stream the data on or we pick and lift and shift it all the way onto the training instance. Our data set is relatively small again, so we'll just use file mode and our S3 output location, and that's it. All right, those are the only things we really need to specify. And then we set our hyperparameters, right? So these are specific to the algorithm. They're in the SageMaker documentation. If you're ever interested in, reading up on these by the built-in algorithms, right? We have, we can go to blazing text and we can go to hyperparameters and see which ones are required and which ones are what the default values are and things like that. For this case, we can talk through some of the ones that we're specifying. We're setting it to use batch skipgram, which is a certain variant of word2vec. We're going to run 5 epochs, which is 5 full passes through the data set. We want only words that appear 5 times or more. We use some network parameters like learning rate that we set here. Again, these are all tunable, and these are things that you might use SageMaker automatic model tuning for. We're going to talk through an example of that next. But for these, we'll just use the kind of values that are already specified here. So learning rate, window size, how many words to look around each word, batch size. Again, a lot of these can be tuned. One of the unique features that this has is subwords. So if you're training on a language that has a lot of really long words like German, where you kind of smash together smaller words to make one big word, this will actually break up the words into smaller character components and then use that to allow you to try and predict the meaning of new words that you've never seen before and never trained on. So you can get embeddings even for words that you haven't seen in your corpus, which is pretty interesting. So we set those and that. We set up our training path already once. We're going to add a little bit of metadata to that, so let it know that fully replicated. That means we're going to bring all our data to all our instances. If we had multiple keys within S3, we could shard them across and share them across the training instances, but we just have one file in this case. It's text plain data, and then we just set up a train channel. So train is the channel that is being expected. All right. Now here's where, again, we start to look like scikit. We do .fit, right? So we take our estimator that we created above that specified all the information about hardware and which algorithm we're going to use and what hyperparameters we want, kind of in a scikit way, and then we do .fit and we point our inputs to an S3 path, right? And in this case, what's going to actually happen is once we run .fit, we're going to go provision new training instances. We're going to load the Docker container to those training instances. We're going to load the data from S3 into the Docker container. We're going to train. Once we start training, you'll actually notice all the logging from that algorithm gets spit to both CloudWatch and your notebook instance, right? So you can see here, we've got these logs that have started to trickle in from our training job. And we actually vary color across the different instances, because different instances could be logging different information. And so you get all of this. These logs are kind of held in CloudWatch, so you can kind of store them for perpetuity. But you also have them here, so you can see and understand what's going on in the training algorithm, watch its progress over time, check throughput. So we're doing 4 million words per second, which is pretty blazingly fast. And then in this case, we do a little evaluation on a custom holdout data set. So as I mentioned, the embeddings that we have should represent very similar words, should have similar in the same feature space. So there's actually a special data set that we have called EN-WS-353 that's used as a benchmark for word similarity. And so we can say how well we did, how similar our vector pairings are, our vector representations are relative to similarities in words, right? That are known from expert review. And so that runs for about 295 seconds. And so that's the billable time anyway. Again, we have to provision instances and tear down clusters here, so it kind of takes a little while to run in the background. But once you have that, now to put that behind a real-time production endpoint, it's as easy as just running .deploy, right? And so that .deploy, we specify how many instances and what instance types, and that sets up a real-time production-grade persistent endpoint, right? So we've trained our model, and we've gone to a hosted model in production that fast with just one line of code, right? We just .deploy that model that we just .fit. And again, that's going to go provision instances. It's going to take the model artifact that you just trained from S3, load it in, and prepare any prediction code, prepare the web server to take HTTP post requests and produce predictions back. And so once we've done that, we can now take a look at what predictions we would generate. So we've got this .predict functionality. This could be, you could theoretically do this with like a curl or Postman or anything that you want to do with an HTTP post request. We also have a little .predict function that'll serialize and deserialize the payload for you. In this case, that's what we're going to use. So we've got these two words, awesome and blazing, and we're going to send them at our endpoint to get a real-time prediction for what their embeddings look like, right? And so you can see we get a list back of 100 numbers. That's the word awesome in the embedding space. And that's the word blazing in the embedding space, right? So you can use that for integration into any real-time service that you may have. But now let's go through and actually kind of evaluate the results. It's nice to kind of see that functionality right in front of your face, to have like a live real-time endpoint. I think I actually have one still up and running here. Let me see if this works to actually run it, just so that you can get the, yeah. So there's the flavor of it, right? So you'd have a separate service that's pinging this with different words and providing you real-time embedding values that you could then use as either a pre-processing step to do a nearest neighbor lookup, or you could use it in a variety of different ways in a production application, right? But you can see just how fast it is that we're predicting off a real-time endpoint and getting back real responses from our predictions. So now the next thing we'll do is we'll take that model artifact, like I mentioned. After we've trained the model, we send the model artifacts back to S3. So that's what we're going to do here. We're going to go ahead and download that model data and untar zip it. And we get 3 resulting files coming out. So eval.json, vectors.txt, and vectors.bin. Eval.json is that evaluation value that we talked about before, so we don't need to kind of go into that in more detail. But vectors.txt is what we're probably really interested in, and that's a lookup of each word and its vector embedding space. And so we might want to look at that to make sure it makes sense. So we'll grab the top 400 records out of that. And because it's in a 100-dimensional space, we're actually going to reduce it even further. So we're going to calculate embeddings on our embeddings with tsne. So tsne is a very popular kind of nonlinear technique to just visualize high-dimensional data. And so we do that, and we can see here that let's make that smaller. All right, that's a little bit better to look at. We can see this is a map of our top 400 most popular words, right? And you can see that words that mean something similar or have a lot of similarity to them appear nearby one another. So all the individual consonants are appearing over here. Team, player, company is down here in one little section. Case, court, law show up together. somewhere years, year, day, days shows up. English, British, American, America. So you can see a lot of words that mean the same thing are showing up in the same thing. So that means in the same space. And so that means that our embedding algorithm has done a good job of sort of understanding these words, understanding what they may syntactically mean, and being able to find similar words. In this case, we've got a bunch of words, and now we have their numeric vectors. There's a variety of things you can do with that. It's a thesaurus, first of all, I guess, right? You could find similar words and by looking at which ones are close to one another. But you can also use it as pre-processing for natural language processing and sentiment to reduce the dimensional space that you're going to build a subsequent model in. I've seen people use Word2Vec for recommendation problems, where instead of passing in sentences of text, you pass in movies someone has bought, and then you do the embeddings on the films that they've watched. And then films that are similar show up in the same space, and you can use that for kind of recommendation of new products and things like that. So kind of a lot of different options. I wanted to kind of show this just to get people kind of thinking about embeddings, because we'll actually use them in a later example. And then also just to kind of show what it looks like to take a built-in algorithm and how little code that actually is in order to make it kind of run from estimator to real-time production endpoint. Okay. Cool. I'm gonna stop right now and take questions. So please do. Yeah, there's two different ways. You can do your manipulations, well, three different ways. You can do your manipulations in the notebook instance itself. If your data set isn't enormous and it can fit in a single instance, you can definitely do your data manipulation there and then send it to S3 and then train. The other way you can do it is do it in another service like Spark EMR. And so we talked about the SageMaker Spark SDK a little bit. That allows you to kind of build a pipeline within Spark EMR and then integrate a SageMaker estimator into that so that you can use training or SageMaker hosting from there. Or you can just use Redshift or any of the other kind of services that we have and just dump data into S3. S3 is kind of a universal transition medium of data. And then the last one is if you bring your own container, which we'll kind of show a little later, you can actually do all the pre-processing in the container itself. And so you can have a whole bunch of pre-processing logic to take in a bunch of raw CSVs, convert them all types of ways, and then run training all within that same training instance. There's nothing that says that training instances can only do training. They can also do pre-processing. Other questions?
So one question I asked is, in this example, you are training the model on the same notebook. Let's say that I want to have a lighter notebook, let's say something like MRT, because I want to have that notebook always open, and I'm going to train the model on some P2 instance.
Yep.
So in that case, and I want to use, let's say, some specific version of Keras or TensorFlow. So how easy or complex would be that?
Yeah, sorry. Maybe I didn't make that perfectly clear. This is not doing any work on the notebook instance except for orchestrating, right? So when I specify the hardware type, I'm specifying two instances, a C4 2x large, and that's where all the training is occurring, and that's what SageMaker is doing, spinning up a completely separate training instance for you to train, and then cascading things back to you when you do .fit, right? So you're pointing to data in S3, it's doing that separate training instance. You're just orchestrating from your notebook instance.
And do we actually copy the data to the temporary instance? How does the workflow work? And then we just delete the data from the experiment?
Yeah, we handle all that for you. So that's one of the things that SageMaker handles, right? That's why you pass in an S3 path here. So this data channels is the path in S3 that you want to fit the data on. And then SageMaker handles sucking that data in, doing the processing on it, and then tearing down that cluster afterward. all handled for you. Questions? Yeah. Yep. Yeah, so when I do .deploy, I stand up a separate instance of ML_M4X large that's persistent. As long as I do .deploy, I should mention that at the bottom here. I have this delete endpoint cell. I haven't deleted my endpoint in this case yet, but at that bottom, that delete endpoint is what gets rid of this otherwise persistent resource. So always make sure if you're ever playing around and you want to deploy something and you don't intend to actually use it for production use cases, make sure you delete your endpoints, because unlike the training clusters where we spin the hardware up for you and then tear it down when we're done training, the .deploy spins up a live persistent endpoint that has some number of instances behind it. This could be 1 instance or 10 instances. You can set up auto scaling for it and things like that as well. But they're just there ready to take HTTP post requests. So when I do this .predict here, that's all I'm doing is an HTTP post request to a REST API, right? And getting back a prediction from my model, right? And you can always track your endpoints over here, right? So if you go back to SageMaker, I've created a couple of them here because I was testing things around this morning. So you can see this is that blazing text endpoint that we created as part of that example notebook, right? And you can look at it and delete it here. You can, check CloudWatch logs on it, a variety of other things, right? Yes. Typically how you'd call it would be by setting up a predictor, right? You don't have to necessarily train to have a predictor. You can set up a predictor independently of training. And then if you could use Python to do that, or you would use the AWS SDK, and in there's an API to invoke the endpoint. You can actually, like I said, use Postman or curl or something like that to actually do the HTTP post request. It requires you to use kind of SIG-v4 authentication and things like that, right? That kind of goes a little deeper than we wanted to go here, but for the most part, we encourage people to use the AWS SDK and invoke the endpoint through the API that exists, but you can hit it in other means as well. Yep. Oops. Import, export. You want to export the notebook or you want to export the data? Okay. Want the notebook? Yep. Notebook we can just export notebook as. Yep. Yeah, so we can just grab that, PDF, etc. You can always, save notebook as or save notebook. You can change things there. You can use a variety of different utilities that they have to do, like NB convert. We'll convert it into a .py file if you wanted, things like that. So there's a variety of functionality within Jupyter, but the export notebook as is the just easy way to point and click. Yeah. Yeah, typically, there's Git on the notebook instance. So you can just kind of go to a terminal and use Git. And some people do that. You can integrate with code commit. And people do that for version tracking. Git has reasonable support for Python notebooks. I've heard mixed results between data scientists as to how much they like using version control versus not. And so, there's also the possibility of, all of this code is just Python, and so if you wanted to just write .py files and have those in version control and have the notebook be something more experimental, you could do that as well. There's a question in the back? Yeah, you could go through API Gateway to contact the endpoint if you wanted to. And some people do that for certain types of authentication or control and things like that. So we've had customers doing that.
Can we support multiple endpoints within a particular model? And can we parallelize the model prediction within the machine that we are calling the endpoint on?
Yeah, so you can put multiple instances behind a single endpoint. You could deploy the same model to multiple endpoints. I'm not sure if you'd necessarily want that, because then that sort of complicates the invocations that you'd have to do. Whereas if you just put multiple instances behind the same endpoint, you can scale, right? It'll use the different instances efficiently to make sure that if one's busy, the other ones will be used, right?
My question was that, let's say the machine has 60 cores. So rather than spinning another machine, is it going to make sure that it's using all 60 cores?
Part of that's on the algorithm author to do, right? So if you're to bring your own Docker container and you didn't set it up that way, no. But if you have something like GUnicorn that has different numbers of workers and things like that, then there's flexibility, I guess, in how you want to use your system resources before you say I'm busy. Yeah. Right. So you can always delete your endpoint from the console, and so you can delete it and then try and redeploy it if you like. The other option is I mentioned that you could actually you don't have to go from estimator to deploy. You can actually create what's called a real-time predictor, and that functionality exists in the SageMaker Python SDK. We'll see it later in one of the later examples, not included in this one, just for simplicity's sake. Right. Cool. Let's charge on through to the next example, and then after that, maybe we'll do a break after that, and then we'll do the last example. How does that sound to people? Good? Okay. Awesome. Okay, so next example is TensorFlow. Okay, so let's do this. And we'll duplicate so that I can do my big show. There we go. Okay. So the next example that we'll go through is this TensorFlow automatic model tuning example, and we really like TensorFlow at AWS. It's versatile, it's popular. A lot of our customers like it, and so we wanted to make sure that it was one of the first things that we had built-in support for within SageMaker. And so right when we launched, we had a pre-built TensorFlow container that allowed you to write your TensorFlow code and submit it to our container, right? So that rather than having to think about bringing your own container and thinking about how to make TensorFlow work with distributed managed training and get TensorFlow serving to work with SageMaker hosting, that would all kind of be prepared for you. And you would write a small number of functions, bundle those up into a script, and then send us that script, and we would just run the script for you with our TensorFlow container, so that you don't have to kind of think about managing, all that kind of functionality, as well as versioning and maintaining that on an ongoing basis. And so those are nice. Those are available. They're open source as well, so you can actually go see what we have there: SageMaker-TensorFlow-container. Right, so we've got that available on GitHub. You can go see our Docker files, see how we've built it, understand how we've kind of set up the code to work there. The right one here? Okay. Good. So this example notebook is going to use that pre-built TensorFlow container. We're also going to use automatic model tuning. And automatic model tuning is a really flexible means of doing hyperparameter tuning for your models. It can wrap around the built-in algorithms. It can wrap around our pre-built deep learning framework containers. And it can wrap around your own container. So it doesn't really care what the algorithm is, as long as there's a list of hyperparameters that it can specify and a output metric coming into CloudWatch logs that can tell it whether it's doing better or worse across training jobs, right? And so that's a nice functionality, kind of blend those two things. And we're going to start with just kind of a really simple problem in TensorFlow here. We'll just do MNIST, and we'll fit like a very simple convolutional neural network with TensorFlow, and then use automatic model tuning to see how that kind of changes the results we might get. So again, it's our standard setup. We've got an S3 location and an IAM role, and we import some libraries. Don't worry about these warnings. In this case, these warnings are driven by a very long NumPy GitHub issue that people who really don't like warnings in their code are very upset about. But it's fine. Everything will function as normal. We'll get our data set. So for those of you guys who aren't familiar with MNIST, it's probably the most well-known, one of the most well-known machine learning data sets around. It's 28 by 28 pixel black and white images of handwritten digits, 50,000 training images, 10,000 test images, and obviously those images fall into one of 10 classes, the digits 0 to 9, right? So we'll go and download that. Done. Let me switch back over here real quick. So here's a little screenshot of what that image looks like. So here's the number 3. You can see it's 28 pixels by 28 pixels, and it's an handwritten digit, right? We'll set our inputs up. Again, we're just going to upload the data to a location in S3, and there's the location in S3. Now we'll have to write that TensorFlow script that I talked about. So this was our TensorFlow code, and we tried to make it as kind of natural and idiomatic as possible. So we use the concept of TensorFlow estimators, and then that allows you to kind of build a lot of different things. In this case, we're going to build a convolutional neural network. So for those who aren't familiar with convolutions, we got a couple links in this book that kind of are nice ways of looking at and thinking about convolutions. Basically what a convolution is a small grid, and you do matrix multiplication as you pass this grid across the image, right? And as you're doing, you can see as I move this grid over each subsequent set of pixels, I get different outputs there based on the matrix multiplication that's being done between the kernel, or the filter, I guess, of the convolution and the image, right? And so you can create a lot of different interesting kernels. So let's do right Sobel, right? So right Sobel is going to highlight the right edges of this image that we're looking at, right? So you can see anytime the image kind of transitions from one thing to the next, the right Sobel catches that as long as, and makes a really clear distinction there, as long as it's on the right side, right? Whereas if it's coming from the left, you don't see any real distinction. But if we do like a left Sobel, now you can see the lines whenever you see changes on the left side, the convolutional filter really highlights those. So the point of this is that when you're building a convolutional neural network, you're learning what these values should be in this convolutional filter. And you're doing that so that you can ultimately here we go. There we go. You're doing that so that you can ultimately understand more information about what's in this image. So you can see I've drawn the number 7 here, and this is what a kind of a convolutional neural network looks like actually in action, right? So we create all these, whoops, going in too much. We create these different filters. So in this case, we have 6 different filters in our first layer of our convolutional neural network. And the first one is learning something about kind of bottom lines. And this one's learning something about some outliney stuff. This one's learning interior outlines, maybe. Like that one's exterior outlines, maybe. Right? We can't really tell exactly. I mean, it's the neural network's job to learn these based on the training data it receives. But what's going to come out is the fact that this uses one convolutional filter, this uses a different convolutional filter, and this uses a different convolutional filter. And we're going to learn something about the image by applying those to our input, right? Each of those, once we've done that, goes through a mapping. So we do some max pooling, and then we do, that shrinks our image space down from 28 by 28 to a smaller space. And then we do another set of convolutions, and then we do another max pool, where we again take a subset of something like 4 images in a grid and take the max value to shrink it down more. And then we eventually end up with something that looks totally unintelligible, but has captured a huge amount of information. Right? We've captured this information about what an edge is and what a curve looks like, and why those things would be helpful to then predict what digit it is. Right? So that's the real key here, is that we use this balance of convolutions, max pooling, and then a fully connected layers here for a neural network to get a prediction for what that image looks like. Right? Let's go here. Okay, so how we specify that within TensorFlow, or within our TensorFlow script. Let me. Okay, good. Okay, so we define a model function. This is pretty standard for TensorFlow estimators. We handle our hyperparameters at the beginning. So we have an argument into that model function called params, and that's just a dictionary of values. These are going to actually be passed in when we create that SageMaker estimator, the same way we ran that .set hyperparameters function in blazing text. So we'll specify learning rate, the first kernel size for our first convolutional layer, and then which activation function. I kind of randomly picked those hyperparameters. We could tune a lot more. We could tune things like dropout and convolutional filter size in other layers, things like that. I kept it relatively simple just for the purposes of illustrating hyperparameter tuning. And then really we start just defining our layers, right? So we take in this 28 by 28 pixel map. We create a convolutional layer that's first. We have 32 of them. And they're going to be set by our hyperparameter value in terms of size. So, the convolutional kernel here right now is a 3 by 3. We could have that be bigger. It could be a 5 by 5. And you can kind of tune that to get different performance out of your task. So. that's what we'll set there, and then a convolutional activation function. So you have these different, after you do each sort of matrix multiplication in a neural network, you usually do an activation function to add some form of nonlinearity. This is necessary. It's not necessarily necessary for every convolutional neural network, but it's necessary for any kind of feed-forward neural network so that you're not just doing a bunch of matrix products that you could drastically simplify. But an activation function we'll talk a little bit more about later on and see what those look like. Then we do our max pooling layers. Then we do our convolutional 2D layer. Again, this is all standard, TensorFlow sort of syntax. We do a dense layer at the end, and then a dropout layer, and then we do our prediction of which digit it actually is, right? So 10 different units. Here's the estimator. We have different modes of train and evaluation. So in the train case and the evaluation case, we set up a global step, and this is how we do parallelization within SageMaker, right? We've taken care of setting up the hyperparameter server or the parameter server for you, so that you don't have to think about that. We've set that all up. You just have to define your global step, and then in your optimizer, we're going to use Atom, which is a way that we find those weights of the convolutional kernels and of the fully connected neural networks. We're going to minimize our loss, and we're going to pass in that global step, which is going to allow us then to do training in distributed fashion. Right? We also have some serving functions here. We don't need those. This is actually, I kept them in because it keeps it consistent with the other TensorFlow examples, but you don't actually need to do that because we're not going to do any serving for this example. Should do that. And then we can do, here's where I talked a little bit about how you can, in the container, do pre-processing. So in this case, we have an input function, and it takes in different data sets and does, in this case, super light pre-processing. We have other examples that do more pre-processing within the container, but you can do it right here in just a function that you've created called input function that train input function then calls and runs on TF records, and then that data gets passed into your model function for when you're actually trying to train your data, right? So it's just kind of pre-processes. Any pre-processing steps that you'd want could go in there. So now we'll actually go about and do the training. It differs a little bit from the last one in the sense that we don't provide an image, a Docker image. This time we provide an entry point, right? So this is the script. The TensorFlow constructor here in Python comes from that SageMaker Python SDK, right? That SageMaker Python SDK has a special, I can get to it, has a special constructor within it that knows which container to point at and how to do the orchestration of sending in that .py file and making it work like a script that this container is going to run and execute, right? The rest of it stays very similar. So IAM role, information about hardware configuration. So we're going to train on 2 instances, C5x large. Again, these are transient instances. They're just going to be spun up for the lifetime of the job. And we're going to specify our hyperparameters here, so learning rate and convolutional kernel size, right? And then we'll run, yep. That's correct. Yep. That's how we handle distributed training in TensorFlow, right? So we handle the parameter server for you. You don't have to think about orchestrating communication across nodes or things like that. That's one of the advantages of using the pre-built TensorFlow container. Yeah, so the global step is something that gets used in the optimization functionality, and it's something that's sort of native to TensorFlow. So I have a link to TensorFlow documentation there if you care to learn more about how to do distributed training in general in in TensorFlow. Typically, it sort of requires you to set up this parameter server, and then the global step can take advantage of those things. But distributed training in TensorFlow isn't necessarily a topic I could I could go into in this particular workshop. It does take a little bit of effort, and that's why we tried to make it drastically simplified here, so that you just pass that global step to your optimizer.